Section 6.4, a whole new way of looking at functions, parametric functions. So parametric is referring to a parameter, and a parameter is basically saying, well, as that parameter changes, all other things will change. For example, if you see my hand move, that means that time is passing. We don't see time passing, but if time doesn't pass, nothing can move. So time would be the parameter. Now to an actual example. So suppose that you have a nice little circle, the radius is 1. Then what's the equation for the circle? Well, if you've had pre-calculus, then hopefully you know. Otherwise, I just have to tell you the equation is x squared plus y squared is equal to 1. So this is the pre-calculus way of looking at it. This has no parameter in it. And in fact, time does not pass. But in reality, suppose that there is an object going around in a circle, like that could be a nail in my tire, and as I drive down the road, the nail is going around and around and around and around. So there would be the parameter of time. But in here, you can't see any time. There is no time. How do we introduce a parameter? Well, this formula right here has the equivalent in trigonometry, which is sine squared plus cosine squared is equal to 1. So in other words, somehow sine and cosine can also create a circle. Well, this is in the x spot, and this is in the y spot. So what you do is let x equal, now they both have squares, so I can just take that off. Let x equal sine. And then we're going to use the parameter t as if t stands for time. And then y is going to equal cosine. And that is our first parametric function. Also notice that it starts with the word pair because they always come in pairs. X and y, you have to have an equation for x and equation for y. So this whole thing altogether is our first parametric function. Now you can actually graph this on the graphing calculator. The first thing to do is go right here to mode. And so far this semester, we've only been using the function. Oops, I hit the wrong button. Change the mode. And instead of function, change it to parametric. So just hit enter. And now when you go to y equals, it's no longer going to say y equals. It's going to say, what does x equal as a function of t? And what does y equal? So x equals sine of t. Y equals cosine of t. So when I use this button now that always used to be an x, well, because I changed it from function mode to parametric, now it's going to use t. Now go to the window. And because these are trig functions, I should have t go from 0 to 2 pi so that it draws the whole picture. This step, I'll explain that in a moment. But if it says 0.13, whatever, just leave it like that. If it doesn't, you could just type in 0.13. And it's a circle with a radius of 1, so I'm going to need x to go from, I'm going to put -2 to 2. That way I'm sure to see the whole thing. And then y is also from -2 to 2. And then go to the graph. And it draws a nice perfect circle. And your brain should be saying, that doesn't look like a circle. That looks like an ellipse. I agree. But it's going out to 1 and 1 and 1 and 1. The reason it doesn't look like a circle is because this screen is a rectangle. So actually everything we look at has been stretched sideways so that it fits a rectangular screen. In order to fix that little problem, you just go to Zoom, and number 5 is zoom square. So it then adjusts the screen so that it would be squared off. And then it makes a nice perfect circle. Not only does it give us a nice circle and it has time in it, there's also a direction that this circle goes. With this circle, I don't know if it was drawn this way or if it was drawn this way. But with this circle, there is definitely a direction. So in order to see that, go back to Mode. Go back to Window. And now this T step. So basically it means it's going to start with a 0, and then it's going to plug in point 13. And then it's going to go to point 26, and then point 39, and then it's going to connect all those dots. So if you make this a smaller number, then it's going to draw the graph more accurately, but it's going to take it longer to do it. So if you change that to a 0.03 graph, you could see it goes slower, and you could see where it started and then what direction it went. So the parametric has a lot more information. So this was the start, and then it went around this direction, and then we put little arrows on there, and the little arrows are called the orientation. So what direction did it go? And then it continued and finished the circle. And the orientation is that it went clockwise. Now let's try another one. How about something that's not a circle? So I guess I didn't label that one as example number 1. I'll label this one as example number 1. So what if it's x equals 6 sine of t, y equals 9 cosine of t? So we're going to sketch the graph. With the orientation. And then we're going to eliminate the parameter. So eliminate the parameter basically means you're given this that has the t in it, go back to this that doesn't have the t in it. So take it from a trig problem and change it back into a pre-calculus problem. But first, sketch the graph. And for that, we could use the graphing calculator. Y equals, so 6 times sine, so I just need to put second insert a 6. And for this one, second insert a 9. So that means the x values are going to go out to 6 and the y values are going to go to 9. So I'm going to change the window, leave all of this, but x, I'll just go from -10 to 10, and y from -10 to 10. And then graph it. Now this one looks like a circle, but again, the screen is distorting it. So then go to zoom number 5. And there we go. That is an ellipse. So the graph is going to be, this is 10, so on the y-axis it's going up to 9 and down to -9. And then this is 1, 2, 3, 4, 5, 6. On the x-axis it's going to 6 and -6. And then it drew a nice perfect egg-shaped ellipse. And I was so excited about the ellipse, I forgot to pay attention to the orientation. So all I need to do is change any one of these numbers. So I'll change this to a 0.04. And that will force it to regraph it So the orientation is the same. So this was the start, and the orientation is the same as the last one we did. It goes this direction. So that sketched the graph with the orientation. Now eliminate the parameter. Well, with eliminating the parameter, two ways to look at it. One is, if you know some pre-calculus, the equation for an ellipse basically looks like this. Except the x squared needs to be divided by something squared, and the y squared also needs to be divided by a number squared. That's the general equation of an ellipse. So this is basically saying x divided by something and they got squared. This is saying y divided by something and they got squared. So how could we get x divided by something? Just divide both sides by 6. So x divided by 6 is equal to sine of t. On this one, divide both sides by 9. Y divided by 9 is equal to cosine of t. Next, they need to be squared. So square this equation on both sides. Square this equation on both sides. And then we need to add them together. So then add the two equations. On the left side, it's going to have x squared over 36 plus y squared over 81. And then on the right side, it's going to have sine squared plus cosine squared, which equals 1. And that is the equation of an ellipse, but the parameter has been eliminated. Now, for example number 2, how about if it's not sine and cosine? So how about x is equal to tangent of t, y is equal to the secant of t. So again, we're going to graph it and then eliminate the parameter. So x is equal to tangent of t, y is equal to secant, and my calculator doesn't have secant, so I need to change that to 1 divided by cosine. And I don't know exactly what to do for the window, so for right now, I'm just going to leave it the way I had it and go to graph and see if I can see what's going on. That is what's called a hyperbola. That is also an example where the calculator is making a slight mistake, because a hyperbola has two branches, one that looks like this, and one that is symmetric and looks like this. And then there's an asymptote that goes like this. And then the hyperbola will get closer and closer to the asymptote. I should also find this point right here. So if I go to trace, it happens to be on that point right now. So that's when t equals 0. So that's when y equals 1. And then this point, because it's symmetric, must be that y equals a negative 1. All right, there's the graph. What about the orientation? So change the window and change one of these numbers so that it has to regraph it. So as it graphed, it did this first of all, and it went in this direction. And then it came and did this branch down here, and it went from left to right. And then it did this part last, so it was graphing from left to right. So this goes from left to right. This one also goes from left to right. Now what about eliminating the parameter? Well, I could use a trig identity. There's a few to work with, but I know that 1 plus tangent squared is equal to secant squared. So in other words, if you change the thetas to t's, 1 plus tangent squared t equals secant squared t. And now since x is equal to tangent, take that x and plug it in here. So that would say 1 plus x squared. And since y is equal to secant, then substitute a y here. And there, we actually already did it. That's eliminating the parameter. Now that's not the usual form for a hyperbola. So to put it in its usual form, you put the x and the y on one side. So then that would be y squared minus x squared equals 1. So that's the traditional form for a hyperbola. So for an ellipse, it's x squared plus y squared equals 1, and then it can have these numbers in here. And for a hyperbola, it's either x squared minus y squared, or it's y squared minus x squared equals 1. And whichever one's the positive, that's the axis that it's hitting. So this one has y positive, so then it's hitting the y-axis. It's not hitting the x-axis. Then let's try one just a little more challenging. Example number 3. So for example number 3, how about if x is equal to cosine of 2t and y is equal to cosine of just t? So to begin with, graph it. So erase these and go with cosine of 2t and cosine of t. Now cosine, the biggest it gets is 1. It ranges between 1 and -1. So I can change the x-axis to go from -1 to 1, and the y-axis also -1 to 1. And then go to the graph. That looks like a parabola that's going sideways. Okay, once again, I forgot to look at the orientation, so let me change this so that it regraphs it, and it goes basically from the top to the bottom. All right, now eliminate the parameter. Well, with this, we could use a trig identity. So x is equal to, and then cosine of 2t, so that's equal to cosine squared minus sine squared. And then the good news is, you could, since y is equal to cosine, you could plug it in for that. But then we don't have anything to plug in for this. So we could then replace sine squared with 1 minus cosine squared. So this will be a -1 or -1, and then this negative and negative makes a positive cosine squared, with another one means there's 2 of them that are cosine squared. Now Since y is equal to cosine, plug that in right there. So y goes right here. So x equals 2 times y squared minus 1. And there we've eliminated the parameter, and when one variable is squared and the other is not, that makes a parabola. Cha-ching! And now for example number 4. But we're not going to do the same thing. We're going to do something slightly different. Find the x-intercepts and the y-intercepts. So where does it cross the x-axis and where does it cross the y-axis? And this function is going to be x equals 1 minus sine of 2t, and the y part of it is going to be cosine of t squared. Clear out the old function. Next, it's 1 minus sine of 2t. And the y part is cosine of t squared. And then, what does that look like? Whoa, 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 whoa. Okay, that's too many answers. Let's just narrow it down to 0 to pi. So I need to change the window, go from 0 to pi, and then make the x a little bit bigger. So how big could x get? So this could become a -1 and a -1, so it could be as much as 2. And then cosine ranges between -1 and +1, so the y's are actually fine. That is an interesting function. So parametric functions actually can be used for all kinds of different things. So for example, I'm trying to find something with print on it. The 6 of clubs. So what makes these shapes inside the computer are actually called Bezier settings. So they're parametric functions that when you graph them, they make these shapes. So they can make all kinds of things with parametric functions. Okay, x-intercepts. So there's 1, 2, 3 x-intercepts. And it looks like there's 1 y-intercept. So for x-intercepts, you let y equal 0. For y-intercepts, you let x equal 0. So for the x-intercepts, you just use this equation right here and substitute a 0. And then this part is saying if you look at the regular cosine function, then when is it equal to 0? So there's 2 places where it equals 0. One would be pi over 2, and this one would be 3 pi over 2. Now when I was looking at the graph a moment ago, I was counting, and for x-intercepts, there's 1, 2, 3. So we actually need 3 answers. So if you continue this graph out, there's going to be another answer right here. This is 1 pi over 2. This is 3 pi over 2. So following the pattern, this is 5 pi over 2. Now those are not the final answer because this says t squared. So t squared would equal pi over 2. T squared would equal 3 pi over 2. T squared would equal 5 pi over 2. And then all we need to do is take the square root of each one. So the square root of pi over 2, t equals the square root of 3 pi over 2, and t equals the square root of 5 pi over 2. Now, we need to do two things. Check and make sure that these are correct. And x-intercepts and y-intercepts are actually points on the graph. So we need, what is this actual point right here? So trace and plug in the square root of pi divided by 2. And that point says x equals a 0.407 and y equals a 0. So this one corresponds to 0.407, comma 0. Now, put in the square root of 3 pi divided by 2. That's that one over there. And then it says x equals a 1932 or 1.932, comma 0. And for the third one, that will be the square root of 5 pi divided by 2. So that's at 1.627, comma 0. So now we're done with x-intercepts. With y-intercept, it looks like we're only looking for one answer right there. So for the y-intercept, you let x equal 0. And then I could take this negative sign and add it to the left side. It would become positive sign. And then you could use sine inverse, or you could just look at the sine graph. And where does it equal 1? That's right here, which is at pi over 2. Which is not the final answer because this says 2t, so it has to be 2t equals pi over 2. And then to solve for t, divide both sides by 2, or another way to look at it is multiply both sides by a half. And then this will be pi over 4. And then check and make sure that's right. So pi divided by 4, yep, that's it. And so that one is, it says x equals 0 and y equals a 0.816. And now for the last example of this section. Example number 5. So with all the ones we've done so far, it's been one graph at a time. But now, what if you had 2 of them? And do these 2 intersect? So, graph number 1 is going to be x is equal to cosine squared t, y equals 1 plus sine t. So cosine gets squared for the x part, and 1 plus sine, and for the window, let's see, the y could get as big as a 2. So I'm going to have it go from -2 to +2. I think I'll just go ahead and change the x's to -2 to +2. And the graph looks like, oh, you know what? From the last example, I had it only going from 0 to pi. I need to have it go to 2 pi. and it looks like part of a parabola. Okay, I'll come back to that in a second. Then graph number 2. So this one is defined by x equals a half and y is equal to 2 sine of t. So leave graph number 1 there. And then for graph number 2, x is equal to a half and y is equal to 2 sine of t. And then, do they intersect? It sure looks like it. Looks like they intersect right there and they intersect right there. But remember, with parametric, we also have the idea of time. So imagine, if you will, these are 2 airplanes. So you see the airplanes going through the sky and they're flying, and you think, oh no, this is not going to end well. They're going to crash. And then they go like this. And do their paths cross? Yes. But did they get to the same place at the same time and actually crash? No, because the red one sped up, it went across, and then the black one went across. So they actually did not intersect. So we have to find out, yes, they did get to the same point, and they did get to the same point, but did they do that at the same time? So to find that out, what you do is you put the x equal to the x. So for the x's, I would have cosine squared is equal to a half. And now solve for t and find out what time that function gets there. So take the square root of both sides. That would look like this. And then take cosine inverse. So cosine inverse of 1 divided by the square root of 2 is a 0.785. And if I insert a negative, it's 2.356. So t is equal to 0.785. T is equal to 2.356. Now, if you go to the graph and you trace and put 0.785, you'll see that yes, that is one place where it looks like they intersect. 2.356. Oh, that's the same point. Okay. So we would need to get a different solution. But I want to go on to the y's and then show you the final point. So now set the y's equal to the y's. So 1 plus sine of t equals 2 sine of t. And for this one, we could subtract sine from both sides. This would have 2 sine minus a sine, so that just leaves sine. And then sine equals a 1. Well, the sine graph looks like this. When it equals 1 is right here, and that is pi over 2. So t is equal to pi over 2. Pi divided by 2 in decimal form is 1.571. And none of these times match. So this one would have to match with one of these, but it doesn't seem to. Is the 1.571 even correct? Go to the graph, trace 1.571. Oh, that's not even a place where they intersect. Unless I'm not seeing the whole thing. Nope, that doesn't even look like an intersection point. So the part that I have not really been showing you is, what if you graph the two graphs at the same time? So like I was doing with the two pens, do they actually get to the same place at the same time? So to see that, you can go to Mode and then change this. So sequential means graph one at a time. Simultaneous means graph them at the same time and then see if they get to the same place at the same time. And that sure does not look like it. Now, one other thing you can do to help see is if you go back to y equals and you change this. Blue is fine, but this is what I wanted to change. So just put the cursor on that and move left or right, and then this is the one that I want. So this is basically like a circle or like a baseball flying through the air, and it's going to leave a line behind it. And then okay that. Then change this one to the same thing. And now go back to the graph. So you can see the two little circles did not get to the same place at the same time. They're not even close to each other. So it looks like they do not intersect. So even though they crossed paths, they didn't do it at the same time.